Hello and welcome again to my Physical Science online lecture series. In today's video lecture, I wanted to introduce the topics of electricity and magnetism. Now, electricity and magnetism is a relatively broad subject, as I've said about many of the other subjects that I've covered so far in this course. I want to hit on a few short topics within this subject, beginning actually with electric charge and moving from there into electric force and so on. So electric charge itself is a fundamental quantity. It is quantized. It's quantized for practical purposes in units of the charge of an electron or a proton, although our best theory at this point says that there are subatomic, subprotonic particles which have partial charges, although that just kicks the quantization down by a factor of exactly 3. So leaving aside subprotonic or subneutronic particles, the quarks basically, charge can be quantized in terms of the charge of an electron, which is approximately 1.6 times 10 to the minus 19 coulombs. Beyond that, what I should say about charges is that at the microscopic level, they hold atoms and molecules together. And while gravitational forces hold the universe together on a large macroscopic scale, that the force between charges is many, many, many orders of magnitude greater than the force between masses, than the gravitational force, in other words. So experimental evidence has led us to conclude that there's two types of charge, positive and negative. And so electrons have a negative charge, protons have a positive charge, both have a magnitude of about 1.6 times 10 to the minus 19 coulombs. And the other common piece of subatomic matter is the neutron, which has no charge. The basic law that governs charges force-wise is, for one, that like charges repel and unlike charges attract, and we can figure out what the magnitude of the force between two charges is using what's called Coulomb's law. And that law just states that the force between two charges is going to be equal to the product of those two charges times some fundamental constant, which is sometimes called Coulomb's constant, divided by the square of the distance between the two charges. And Coulomb's constant has a value of basically about 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So if you have two charges of 1 Coulomb each that are separated by a distance of 1 meter, then the force between these two charges should be just shy of 9 times 10 to the 9th newtons. So one way that we deal with electric forces is by introducing a thing called the electric field. And the electric field can be achieved by saying that each electric charge generates an electric field. That field works on any other electric charges. And the field strength can be measured if we know what the charge is and know what the force is by saying that the field strength is force divided by charge. So it has a unit of newtons per coulomb. So that's forces on charged particles. Energy on charged particles maybe is almost the more interesting topic because it also governs or is used to describe the behavior of circuits, of electrical circuits. So the type of energy that acts on charges is sometimes called electrical potential energy. Of course, if you have moving charges, then you also have kinetic energy and so on. But the electrical potential energy is determined using a thing called volts. And a volt is equivalent to 1 joule of energy per 1 coulomb of charge. So volts are equal to work divided by charge, or more appropriately, work is given by voltage difference times charge. So if you move a charge from one point to another, then to figure out how much energy has been gained by or lost by that particle, or to figure out how much work it takes to move the particle from one point to another, you can just find the potential difference between the 2 points and multiply by the charge. The reason why it's so interesting as far as current goes is because, as far as circuits go, is because you can relate voltage to the current that's running through a set of resistors inside of a circuit, in as much as that Ohm's law tells us that voltage is equal to current times resistance. So what are current and resistance then? Well, current is just the motion of charges. Specifically, current gives you how much total charge has moved through a given cross-section in a given unit of time. So usually what that means is maybe you have a wire that makes like a loop, a complete circuit. You take a section of the wire and you ask how many charges pass through this section of the wire per unit time. And that's the current through that section of the wire. So one fundamental law that governs charge is that charge is conserved. That also means that current has to be conserved within a wire. So if you have a circuit and maybe you have 2 branches from the circuit, what ends up happening is that the current splits between the 2 branches, so that the current in one branch plus the current in the other is equal to the total current that went into that branch. And furthermore, the voltage drop across each branch has to be equal if they're parallel branches, because voltage refers to energy, and energy also has to be conserved. Resistance, on the other hand, is basically tells you how difficult it is to move charges through a given section of your circuit. So the higher the resistance, the more difficult it is to move charges through that section. A closely related topic to electricity is magnetism. So if you have a moving charge, then that charge can interact with magnetic fields. So usually a magnetic field is generated by a moving charge. It also affects other moving charges, just like an electric field can be generated by a charge, stationary or moving, and affects other charges, stationary or moving. Of course, you can also have a bar magnet or a horseshoe magnet, which has magnetic poles and which generates a magnetic field without necessarily having a current nearby. The force that a magnetic field applies to a charge is basically the product of the magnetic field strength times the speed at which the charge is moving times the magnitude of charge that you have times some factor that determines the direction of the motion of the charge with respect to the magnetic field. It's actually the sine of the angle between velocity and magnetic field. Magnetic field is actually relatively easy to map out. You just need a compass to do that. If you walk around with a small compass, then the north pole of that compass should always point along the direction that the magnetic field line is pointing in. So actually the Earth has a magnetic field, and the magnetic south pole of the Earth is actually located near the Earth's geographic north pole and vice versa. But that just means that the north pole of any other magnet is going to point towards the north, because opposite poles tend to attract, like poles tend to repel. So as far as magnetic fields go, or as far as magnets go, I should say, there are no known, and according to the theories that we have, there can be no magnetic monopoles, meaning there isn't anything that's quite exactly the analog of a single electrical charge existing on its own in magnetism. South pole and north pole are sort of analogous to positive and negative charges for charge goes with electricity, pole goes with magnetism here. But you can't have a north pole without a south pole and vice versa, whereas you can have a negative charge existing somewhere without a positive charge and vice versa. So actually, magnetism allows us to build such things as generators or motors. So a motor allows us to basically do mechanical work using an electrical current, and a generator allows us to create electrical current by doing mechanical work on a loop. And I think that's quite a bit to digest, so that's all I'm going to say for today's introduction. I hope you enjoyed this video, and I hope that this tour through sort of the terms, if you will, of electricity and magnetism inspires you to read a little bit more about these topics. Thanks for watching.